Microphone doesn't work. Okay. Okay, thank you, everybody. And then we briefly introduce each other. Hopefully, we'll be able to know each other more to this coming the JIP meetings. And then we'll start the presentation by brief overview, how we actually, how and why the hosting this JIP. So the first I'll go over how this OpenFAST-TRUST, the tool has been developed and used in the floating offshore wind turbine design. And also many of you already know OpenFAST, but not much familiar with the TRUST. So I'll give you a brief one slide explanation, what is TRUST, and then quickly go propose the work packages. After then, each work package leader will explain the background and actually the proposal inside the work package. Okay. Next. So actually our company Front Energies, we started 3 years ago. So we got a call from Korean shipyard. They are starting floating offshore wind turbine project. So we asked for the technical support. And the first thing we realized was in floating offshore wind turbine design, especially the substructure hull, time domain structure analysis was needed. And many of the people recommended to contact the DNB, they had the tool, but then we found actually there is a working tool, but it takes too much time. And also for a small company like us, it's not easy to have all the tools because it requires all the FEs of everything using DNB tool. So that's why we actually started the development of our own tool. The principle for the development was we like to fully utilize open source the resources as much as possible, like OpenFAST, and also we like to be agnostic. Any ILA tool or any finite element analysis tool we can use for this kind of structure analysis. So TRUST is actually the interfacing software between ILA tools and then existing finite element tools. And then we actually engage in some the project with the Korean shipyard. And then during the project, we actually keep developed this OpenFAST and TRUST the tool. So then we have about 2 years of the development. So about 1 year ago, we could finally integrate every pieces together. So we gave some training to Korean shipyard. And also we teamed up with their engineers to execute some of the pre-FEED project and also preparation of FEED project. So at that time, still we are mostly using OpenFAST version 3.2. So we had several projects involved, mostly 50 megawatt, and some of them 80 megawatt for the Korean shipyard. And then we actually during the process we closely consulted with the NL people, especially the Jason, Lou, and Amy, and then we got a lot of feedback, and then we found there got to be some improvement in how we use OpenFAST and TRUST in actual industry project. So we worked with the NL team. So we directed the initial scope of work and planning. And then we first presented to the Korean potential, the JIP partners, and also the existing OpenFAST and TRUST users. So there are a long list of some recommended improvement. But the major ones that we put in 3 bullets. The most people in industry feel the OpenFAST is good too, but then it's open source. So, but industry people, they prefer has very definite version of the actual executable they can ready to use. So version control, and also there are a lot of hidden the capabilities. Jason will go over detail, but even for us, who has been using the OpenFAST for 3 years, can use some only the part of the functionality. So the training is also important part of the OpenFAST. That was one of the major feedback. And also because of the industry, people prefer to use some other tools. So they also ask some track record for industry application for like pre-feed and feed project. And the potentially also getting some class AIP for the application. And then another the request was everybody wants to have more the industry-oriented documentation of the work process, how to use OpenFAST and TRUST, and also training, hopefully directly from the actual developer who is familiar with detailed functionality. So that was the main feedback. So based on that, we actually prepared the proposal. But before we go to the proposal, let me give you a brief idea how TRUST works. So TRUST is basically perform the time domain structure analysis for the floating structure. And then it is designed that we capture all the load recipes, such as the wave, diffraction pressure, and then the radiation pressure, and also the inertial load and the connection load from wind towers. So those things actually all common the load recipes in typical ILA software, OpenFAST, OCAFlex, even CFD, they have all those same recipes. The only difference is how they actually identify the load. Then in TRUST side, we actually integrate all the load recipes, but we skip the actually integrating load, but we go directly to the stress level. So rather than to integrate or combine load, we actually combine the stress response for each load components. That's how we go directly to the structural analysis, and it's much faster than typical approach to integrate load and apply to the final element and solve every time step. So that actually made quite speed up all this time domain structural analysis process. So a typical the global structural model, StreamYard, they have about 50,000 elements. The time domain analysis we actually found is even faster than the ILA. The OpenFAST version 3.2 version was quite fast than other tools, but the structural analysis was even faster. And then also because we developed the tool for ourselves in the engineers. So we try to keep the intermediate, all the information like the load distribution just internally. So we actually don't need to save all those intermediate data. So that actually reduced memory requirement on the computer quite a bit. So time domain structural analysis, typical the tools, they need terabytes of data, but we can run it with a few hundred megabytes of just output result. So it can be run on any personal desktop and laptop computer. So that was one of the principle we developed. And also the other extreme, because we use, when we use OpenFAST, we actually have a Linux version. So we can put those OpenFAST and TRUST in the high performance computing environment. So for example, in the recent project, we used some of the supercomputer called Frontera in here in Texas Advanced Computing Center. If you use 40 node, we could do actually the fatigue beans more than 5,000. Actually, it's about close to 6,000 beans within 6 hours. So this actually gives quite a bit of flexibility and also the reduce quite a bit overhead on the structural design process. The structural engineer can focus on structural optimization rather than waiting and spending the tons of time waiting for the analysis result. And also while we are executing the project, we also keep refining the post-processor. So those processes we have now more consistent integrated statistical analysis for all hull mooring and then the structural response. So more detail go over Johan later. So this briefly give you the features of trust. So then going back to the feedback from industry about OpenFAST and TRUST. So we actually listed three major work packages who can give answer to the industry comment. We're still open to your additional comments, but we believe these three topics will cover most of your needs for the industrial application. So work package 1 was reply to the version control and training. So the NREL will develop OpenFAST the refine, also document existing feature. So then we'll actually make the version controlled version of OpenFAST from ILA to structural analysis, and also the part of it. The NREL will embed formal interface with the trust that will make the interface between ILA and time structural analysis more the seamless minimum operation, manual operation. So that is the first package. The second package is based on the developed code. We'll develop the sample case. So basically, we'll demonstrate the readiness of this OpenFAST training package by developing some pre-feed level floating offshore wind turbine design. Some of the decision, what kind of site or what kind of hull model we'll develop, is open to the JIP participants' input. So that's the work package 2. And third work package, however good the ILA tools we develop, still it is based on quite the approximation in physics. So calibration is also a big part of the ILA. Actually, there has been ongoing effort by NL, like OC7. So we actually closely follow that process, and also on top of that, we'll add more functionality in the CFD simulation currently being done by providing fully coupled OpenFAST to model all the DLCs in the design process to make the calibration and validation of OpenFAST in a more close physics. So that's the work package 3. And then each work package, there will be some the detail, the budget and the schedule. But in overall, it will be a 2-year program. And we estimate overall budget about $1.4 million for 2 years. And then we actually asking $40,000 annual fee for each participant. For the academic, there is discount, but for industry partner, we ask that. So which will require about 18 industry participants. So that's an overall view of the proposed work package. And then after this JIP, we like to give you a little visualize what you will get. So we'll provide all the participants through the project whenever we have the fixed version, intermediate, including intermediate versions in each year. We'll provide the version controlled OpenFAST executables with some the test cases. And also the software will include also the trust interface and the trust software and post-process that the participants can try. And also we'll give some training for that part too. And for the trust software, we'll provide the executables interface with OpenFAST. And then at the end of the JIP, we're considering the trust code available in not everything, but whatever ready open source to the public with a certain arrangement. So that's more on detail to be discussed. And then also CIP side, the front energies we have been developing the OpenFAST coupling tools and some of the wave coupling tools. So we plan to hand over to the NREL for the further development because we are a commercial company. We don't have enough resource to keep developing. So we plan to hand over to the NREL for those for further development. And the last item is we'll develop a pre-feed level floating offshore wind turbine design, a complete set of all the pieces involved in floating offshore wind turbine, and then including all the verification of ILA and structural criteria for a given design basis. And then we'll provide all the detailed models and also the training package. Through this package, the participant can learn and also adopt a part of the element in their own engineering process, the tools, and also we'll give in-person training for this developed software tools and design. Okay, that's a brief overview. Okay, this is and also we like to tell you, this proposal is still evolving. We have a series of information meeting. The first coming is in Korea. Is in a few weeks when Joel and I visit Korea, and for European in June time, for better timing for Europe, the Jason will arrange another information meeting. So during those meetings, we'll keep getting input from you, and then we can actually refine the proposal. And also we are open to your suggestion or what will be the next after this JIP. There are several ideas already popped up through the recent discussion, but we are very open for your the suggestions. Okay, then we'll move to the existing features of OpenFAST and TRUST. So
maybe I'll just pause. Yeah, if there's any questions on that background before we give an update on OpenFAST.
Hi, yeah, this is Jerica. I had a question on, just to make sure I understood correctly. You mentioned after the JIP, trust will be handed over to NREL for further development. So does that mean it's going to be an open source tool and part of the OpenFAST package?
That one, we are not still in discussion, but one thing clear is at least one of the working version of Trust, which has consistent one OpenFAST Trust interface, will be released in public. That will be executable, but source code level, we still need to, because we need to clean up the code, and also who will maintain the code. So we still some under discussion. But one thing clear is for the JIP participant, we provide Trust with a full functionality like strength, fatigue, everything. But in public, we still, when the OpenFAST is putting in the open domain, we'll have a limited Trust version, at least to the strength check to the public that they can use new OpenFAST directly linked to this Trust. Is it clear for you?
Yes, thank you.
Yeah, I think we're trying to find that happy balance. I think we're of course OpenFAST is is going to stay open source. There's no change in that. And obviously the big piece missing on the OpenFAST side is being able to do the structural analysis. So we're trying to figure out what piece of the trust, as you'll see, is much bigger than just the structural piece, but we're trying to make at least part of it open source. How to get from that global to local analysis and be able to do things like stress calculations as an open source part. Yeah, the full functionality of trust will probably be still closed, but yeah, we need to figure that out as part of the discussions with the JIP, I think.
Okay, yeah, no, thank you for clarifying. Yeah, I think the more open source tools that are well thought out are definitely better for the industry. So it's good to hear.
And maybe another additional comment is, so even one thing we discussed with Jason is even OpenFAST, it is open source, but then still for industry, parallelly there will be some the version controlled executables too that industry people ready to use. In our case, we are a little in between the development and actual project execution. So we love source code, open source. But then many industrial partners, we saw actually for them, they feel it's also risk. So we actually try to make some mechanism, every release of OpenFAST, maybe source code a little delayed, but very definite version of executable, including all the test set and result that industry people can directly use. That's something we are on the discussion too. Okay, maybe then.
Any other questions? Okay, well, I can jump in here and just give an update on where we are with OpenFAST. And maybe before I jump into the slides, I'll just say, yeah, so the clear feedback, maybe go past back slide. I think the clear feedback we've been hearing over the last several years has been, OpenFAST is great, but you're missing this key thing, which is getting to that detailed local structural analysis. So we've definitely heard this over and over again. I think we've decided within NREL that we're not going to, develop our own FEA code that competes with ANSYS and Nastran, Abacus, and so on. But what we really want is this interface that we can go from the global to the local, and that's basically what Front Energies has done. I think like Front, I think we also want to we're trying to be transparent at NREL and support multiple options. So I think we thought this was a great opportunity to sort of crowdsource a way to make this, structural coupling happen in a reasonable amount of time with a good partnership here at Front Energies. We have somewhat a long-term vision, so I think that's where we're just trying to make that happen. And this JIP was the way we thought about maybe the best way to get this funded, because we haven't been able to find a way to do that through Department of Energy funds at this point. So jump in here, just to kind of give people an update on where we are with OpenFAST. I always start just making sure it's clear on the NREL Department of Energy program side. We do have a range of fidelity that we develop. Obviously, we're talking about here that sort of middle column here. We have OpenFAST, really meant for integrated loads analysis following, say, IEC design approaches. Of course, OpenFAST for the single turbine, and then this matrix kind of expands that into the different directions. So the bottom row is about full wind farms, and so like the natural extension of OpenFAST to the farm levels is a tool that we call Fast Farm, and I have one slide on that. Really, it's how do we handle the wakes in the wind farm? How do we handle shared moorings? How do we handle control at the farm level? We do have a whole group at NREL focused on very high fidelity simulations. This is really about resolving as much physics as we can through computational dynamics. And they have actuator line simulations to full-on blade resolved, surface geometry resolved simulations. Mostly aerodynamic focused, although over time they are trying to develop that further for offshore applications as well. That's still coming, but obviously on the rotor side, we're quite powerful in the farm level. We also have a bunch of tools at NREL on the low fidelity side. Wisdom, there's a series of sort of quasi-study type models, frequency domain models. We also have that at the farm level with our Florist tool. And these are really the kind of models that run, almost instantaneously. So you can do millions of, simulations without really taking any computer resource, really to use the sort of explore design space before you jump into detailed design at the time domain level. And then we also have a tool called WISE that sort of bridges between the design exploration and detailed design, at least at the turbine level. And that's really for like system level optimization. So combining the structural design and the control design in one package. Yeah, next slide. So OpenFAST, I think most people know what this is. It's really our workhorse Aeroelastic code that's, of course, been adopted for fixed and floating wind as well. Two main use cases. One is, running the nonlinear time domain simulations, basically following, IAC or DMV or ABS, BV guidelines to run load cases, compute ultimate fatigue loads. Of course, we stop basically at sectional analysis. So shear forces, bending moments, we don't get into stress strain, hence the need for coupling to say trust. Another feature of OpenFAST is basically to pause the model at any point in time and be able to linearize the model. So we can basically export a linear equivalent, state space model, ABCD type system. And if you can, if you have a linear model that handles all the couplings, you can really understand what's going on. So, we do linearization for things like full system eigenanalysis, mode shapes, natural frequencies, damping. Linear models are great bases for controls design and stability analysis. So that's all there. Next slide. And maybe just to be clear, also, we're aware that there's competing tools in this space. So I think OpenFAST has certain similarities to OrcaFlex. I think relative to OrcaFlex, we're very similar on the floater side. The moorings, hydrodynamics moorings, I think are very similar. But for the turbine, I think we're certainly more advanced, and certainly at the farm level, there's nothing equivalent on the OrcaFlex side. Bladed's coming in from the other side. I think, Bladed's quite strong in the turbine. I think we're very on par with that. Certainly we have them beat on the offshore side. These are just a high level summary of some of the core modules of OpenFAST. On the left side, our main, fluid parts, we have Aerodyne that really has two main aerodynamic options. One's a blade out momentum option with a bunch of advanced corrections, of course, like unsteady aero, dynamic wake, skewed flow, and so on. And we also have a free vortex wake option if you want a bit higher fidelity. Hydrodynamics, our Hydrodyne module, soon to be C-state in there as well. This really has a hybrid combination of potential flow. So if you have like the semi here, you can say, I can either have one big potential flow body or separate potential flow bodies for each column of the floater. And it's a hybrid of potential flow and a strip theory calculations. You can also have alto pontoons and braces basically with an extended Morrison formulation. But it's a hybrid, so you can choose whatever combination you want. Then on the structural side, we have three main structural modules. Elastodyne, sort of our original model, is very similar to the old Flex tool from DTU, whereas has some rigid bodies plus some modal-based tower and blade models. But we understand those are quite limited these days for modern systems. So for the blades, we have an alternative for that called Beamdyne. That's a full geometrically exact beam model with full 6x6 cross-sectional mass and stiffness matrices at each cross-section, handling all the composite coupling terms that you would need, and also full geometric nonlinearity of the blade. And for the substructure, we have our Subdyne module. That's basically a linear beam frame finite element model. We have beams, of course, as the basis, but we also have various joints. You can have pin joints, ball joints, universal joints, also various kind of cable elements like taut lines. And it really, because it's meant for the substructure, this one's purely linear formulations. We have the rigid body rotation plus linear elasticity, But you can basically represent full flexibility of the support structure with subdyne. Different mooring modules. Mooredyne is our closest one to OrcaFlex, basically a lumped mass formulation connected by springs. Servodyne is our main controller. There's some built-in options, but mostly it's an interface either to controller dynamic link libraries or things like Simulink interfaces. Yeah, next slide. Figured I'd just give a quick update on some of the things that have been happening in case you're not fully up to speed on everything. Aerodynamics, we've done a lot of work recently on linearization of aerodynamics. So things like unsteady aerodynamic wake have been in there for a while, but often, or at least previously, we couldn't linearize them. Now we can basically do full state space linearization of these options, and so you can really capture the effect of dynamic wake, unsteady aerodynamics, both like attached flow, Theodorson type theory, as well as linearized models for the deep stall aerodynamics and dynamic stall. So these are really, once now we have it in a linear form, you can do like air elastic stability calculations quite directly with OpenFAST. And then showing the bottom, we've done some recent work also for high skew and high shear. Before, our code is shown there on the solid line really underpredicted power and thrust at high yaw angle. That was pretty important for things like wake steering studies. So we realized our model was basically underperforming from what the other two results there are from free vortex wake. Actually, this is an older plot. We also have blade resolve CFD basically showing that you have less power loss at high skew. And we've changed our BEM solution to get that. Actually, though, that'll be presented here in a couple of weeks at Torque. Next slide. Stepping through some of the stuff here on offshore. First of all, I thought we sort of described that with our subdyne and our hydrodyne, but we can now do full hydroelastic flexibility in our turbine, in our support structure. So again, basically a representation of the beam elements and rigid links and cables. And you can have multiple potential flow bodies, strip theory elements, and really get the full, again, at the sectional level, at least shear force and bending moments if you can represent those as flexible bodies. We've also added constrained new wave options. That's sort of a requirement for fixed bottom systems, and floating, that's like an optional thing. But basically, if you're running like a 50-year severe sea state, you can now basically embed the 50-year extreme wave height into that sea state, and that's fully directional spreading and second order compatible if you want constrained wave options in there now. So that's pretty useful feature if you want to always ensure that a big wave comes through the simulation. We've added wave stretching. That's not too novel, but it's been missing for a while. And then coming out here in 4.0 is a big change, including the introduction of our new sea state module. But we basically now have a full 3D wave grid where the structure will float inside it. And that really gives us the ability to do the proper phasing of waves as you have large displacement. Right now, that's in 4.0, you'll get that release with large surge and sway motion. And then coming soon after that will be support for large floater yaw motion. Blue Wing, I know, just submitted an abstract for NAWIA WindTech, which will present that result. So that's also coming really important for the large yaw for things like, single point mooring designs, or the fault cases where we're going to lose a mooring line and may have large yaw motion. Then finally on the bottom left, lots of new options in there for different floater-based controls, whether it's a buoyancy can or passive, or a TMD, which may be passive or active. Tuned liquid column dampers are in there, as well as things like active cable tensioners. So if you have like tendons that you may want to actively change the length of, or cables in the support structure you may actively want to change, we can do that now as well. Next slide. And then a couple things coming down the pipeline. These are not released yet, but they're coming quite soon. And so I thought these were important to advertise. One is people have been complaining to us for a while as well about OpenFAST losing its speed. When you add beam dyne, you add subdyne, there's lots of degrees of freedom in there, and the model's been getting slower over time. And that's definitely been an issue that we've experienced as well. And so we presented the initial results of this at NVIDIA last year, but the real version's coming here soon in 5.0. But basically what we've done is we've taken the core structural modules of OpenFAST, so beamdyne, elastodyne, subdyne. Right now, it kind of operates at the left where you have separate integrators for each module. And that coupling algorithm is, structure to structure coupling. It works well. It's robust. It's converged. It's stable. However, it does require small time steps, which is not always desirable. And so we've introduced basically a tight coupling option where we take the integrator out of each individual module and we bring it more to the glue code level. And in this case, we've actually introduced a generalized alpha scheme around beamdyne, elastodyne, and subdyne. And what we're seeing with that change is quite a big speed up, factor of 10 on some models, up to a factor of 100 on other models. And so that we're really excited about that. That's going to be a huge change, improvement of OpenFAST. So again, that's coming out in 5.0 release, hopefully later this summer, but certainly in time for the potential JIP we have here. Another thing we're working on is a direct steady state solve. That's basically saying right now, if you have a transient, of course, you can march in time to get that final solution, but we understand it's often desirable, for example, when you linearize, say, I want to know, what happens, for this given wind speed, this rotor speed, what is the steady state condition? And then you can either start your time domain simulation from that or say linearize directly without having to do an initial transient simulation. And so that's another thing we're working on, hopefully coming out in 5.0 release. And then the final thing that's coming down the pipeline, I know I saw Salur and Victor on the call here from Hexicon, and hopefully they're quite excited about this feature, but basically because we have a very modular solution, and aerodynamically, we've already been able to model multi-rotor systems quite well. What we haven't been able to do is the full aeroelastic capability with multi-rotors, and so with this change coming down the pipeline as well, we'll be able to do basically multiple rotors on the same floating platform. Effectively, we just took subdyne and we have multiple interface joints there, each one connected to a different elastodyne body in a tree structure. We can basically have as many of those connections as you want. So showing there the hexagon for Salur and Victor, but obviously it would be flexible enough to handle other configurations. And of course, with the free vortex wake option, you can get a nice aerodynamic solution there. Probably a clap there from Salur, honestly. Anyways, all those are coming down in a 5.0 release later this year. I'll present the multi-rotor stuff here at NVIDIA WindTech. Next slide. I think this is my last slide. Again, just to say that in addition to single turbine simulations, we do a lot of work now on full farm simulations. So if that's of interest to anyone, basically what Fast Farm does is it says each turbine in your wind farm is an OpenFAST model. In this case, we're doing a 36 turbine wind farm at the Waken test site in Oklahoma. So these are land-based systems. But basically each turbine is an OpenFAST model. And in addition, of course, to everything OpenFAST can do, what Fast Farm does is basically allow you to do all the wake tracking. So the wakes come off each rotor and they propagate downstream and impact the next turbine and so on. And we also have like a full control system. If you want the turbines to talk to each other and have a controller connecting them together, that's in Fast Farm. And then we also, like for offshore systems, have like things like shared moorings. So if you want the turbines to connect and pull each other, tug on each other, you can do that here as well. So again, those are all advancements. This stuff is already available, but certainly improvements are coming for Fast Farm as well. Just want to mention that. Okay, I think that's it for me. I don't know if there's any questions on any of that stuff, but happy to take that and move on to the next topic.
May I ask a few questions,
Yeah.
Jason? If you can go to slide 14 or 13, yeah, I don't know. Yes. I read quite a lot about OpenFAST, but I never fully understood what are the degrees of freedom of the floater when you do global performance. Is it just 6 rigid body motions, or
so if you just have elastodyne on and you haven't turned on subdyne, it is just 6 degree of freedom motion. But what subdyne gives you is all the elastic modes on top of that. So if you want the rigid body modes plus the full elasticity of that tower and support structure, so all the bending and flexibility of that semi, you would get that if you turn on Subdyne.
Okay, but does that mean that let's say few natural modes of the tower are included in the as a degrees of freedom of the system, or how does it work?
Yeah. So basically, Elastodyne has basically the bottom of Elastodyne is a 6-stop rigid body.
Yes.
And then we have a tower, and right now the tower and Elastodyne is just 2 bending modes, 4 aft, 2 side to side. We are another development coming. It's not started yet, which is why it's not on the list. But we are adding like tower torsion here soon. But that's an Elastodyne. So if you just want a simple, mono tower with bending and torsion, that's an Elastodyne.
Yeah, sorry to interrupt you. But this, you say modes of the tower, they are dry or wet? Or how they are calculated?
Yeah, Elastodyne, they would be dry. The floater, if it's rigid, would be, you could have the added mass there, but the tower would be dry.
So when you calculate...
But you could also say, I could also turn on Subdyne. And what Subdyne is really just a full finite element beam model of that structure. So beams, cables, and various kinds of joints. And with Subdyne, you can basically we do this Craig Band reduction on it. And you can basically choose however many modes you want of the substructure, and that's then included in the model. Yeah, and those are full hydroelastic modes, so they'll couple with the Hydrodyne module.
Okay, there is my question actually. So when using Subdyne, your hydrodynamics is based on rigid body hydrodynamics.
So it depends on how you want to model it on the Hydrodyne side. So if you want to be potential flow, then you choose how many rigid bodies you want. So a good example would be the semi. Normally how we would model this system right here.
Yes.
Is we would say, these I don't have the mouse here, but the main columns, the offset columns are big and
yes.
They're effectively rigid. Thank you.
Yes.
And so these we would basically say that's basically a rigid body.
Yes.
And hydrodynamically, I would say that's a potential flow body. And so that's how we would set it up. We basically say 3 rigid bodies for the columns with 3 potential flow bodies. And if you want to have hydrodynamic interaction between them, you can do that. But then we would say these pontoons and the braces and all that stuff are likely flexible. And so I would say in Subdyne, you'd represent them as beams. And Hydrodyne, you'd represent them as Morrison elements.
Yes.
And so then it's really a hybrid combination where that's a rigid link structurally, but connected by beams.
I understand. But these 3 rigid bodies that you said, so each of them has his own dynamic database?
Yes.
Which is independent of each other, or
you can include coupling terms or not. So it depends on how you process your hydrodynamic data. If you want to just say there's a cylinder with a heat plate, and that's my hydrodynamic database, you can do that. If I want the hydrodynamic database to have the full coupling, so you have the 2 rigid bodies plus the coupled terms.
Yes, you can do. So it will be the
so that would be like 18 degrees of freedom.
I see. Okay. So that's inside. Yeah. But they are rigid.
For the potential flow bodies, it's rigid. For the Morrison bodies, they can be fully flexible. Yeah.
I mean, flexible in a sense, it's represented by a beam, but the loading is based on a rigid body.
So for the rigid body, for the potential flow, we lump all the hydrodynamic force at a point because it's rigid, it doesn't matter.
Yes.
But for the flexible bodies, like the strip theory bodies, I calculate hydrodynamic loads at each cross section, and I pass them over to the beam elements.
Yes, but this dynamic load at each section, your Morrison equation takes into account just the motion of rigid body.
No,
it takes into account
full flexibility. Yeah, it's sending the hydrodynamic, it's sending the motion, the displacement, velocity all along the element.
I see. So the velocity of the beam includes the deformation velocity. Yes. Okay. And so that means if you use Subdyne with these 3 rigid bodies and the flexibility, you can eventually calculate the wet natural modes of the tower. If you put everything together.
Absolutely.
Okay. So there is option to calculate this natural frequency of the.
Yeah, so the linearization capability of all that allows you to export the equivalent ABCD, and then you can do the full eigenanalysis on that.
I see. And the blades are included in, or it's just lumped mass at the top?
You can do the whole thing. So aero, hydro, elasticity, it's all in the linear.
So then you couple subdyne, elastodyne, and dynamics and everything.
Yeah, it's all coupled together.
Okay, thank you. And slide 16. Yeah, when you said wave loss at displaced position, I didn't understood what you mean by that.
So historically, when we did like potential flow or strip theory, we said let's solve the wave excitation part at the undisplaced position.
Yes.
Now we have a flexible body and we have potentially large motion of that floater. And so what we do here now is instead of basically pre-computing the wave loads at its undisplaced position, we basically define a full 3D grid of wave elevation, wave kinematics, and potential flow. The potential flow is basically a 2D plane of potential flow solutions. So if I here, or if I surge 50 meters that way, I have the solution if it's over there. And so then basically at any point in time now, we just interpolate within that big domain. So we get the right phasing of the wave. Really important if you have large displacement.
Usually you do have large horizontal displacement,
right?
And but that's how it's done in Orcaplex actually. So you have this low frequency and wave frequency, right. But I do not understand. This is all included in your global performance analysis.
Yes.
Everything is in. So I do not understand the need for interpolation. That's because this phasing is related to your incident wave and the relative position. And but this vertical motion, vertical dynamic database is independent. It's I mean body fixed database, and then you just move it by phasing.
For the radiation, the hydrostatics, it's like body fixed, but for the wave excitation, where's the body relative to
absolutely. You need
that's what really changed here is that wave excitation piece.
So but it's just a matter of phase.
It's really a phase.
Yeah, but I do not understand need for interpolation. That's why you just include it in the. But okay, maybe you because then in principle this should be.
If it's like a regular wave, you can probably just figure it out. But with irregular waves, I mean the phasing is all
also irregular.
It's just you should for efficiency. You make it.
Yeah, it's really an efficiency thing. You could shift it over here and then recalculate it all, but we found it better just to pre-populate a database and then interpolate it.
Okay, maybe we can discuss.
It probably depends on how many nodes you have and how refined you are. We found it more efficient to just pre-compute a database and interpolate.
Okay.
So
I do not fully understand. I will ask you later.
And there's a nice paper on it too if you want to.
Yeah. Okay.
Yeah. Anyone else with questions on that stuff? And this little tangent to the JIP, so I think for the sake of time we can move on.
Okay. Okay, so this is good. So I'll explain some feature of the trust suite. So previously, Zhang has introduced a brief introduction to the trust. What is the trust? So trust itself is an integrated multi-physics tool suite for time domain structure analysis. So originally, TRUST was developed for the time domain structure analysis. So at the time, we are focusing on the available data, not generated newly for data. Just for example, there is available ILA data, there is available structure model. Then how can we make a time series of the structural response using the available ILA and the corresponding structure model? So that's a starting point. So we developed some very efficient structural analysis methodology. And eventually we are targeting for the thorough structural assessment without missing any load cases. Because that when you developed this time domain structural analysis tool, at the time available time domain tool was very rare and takes a lot of time. Even some short duration of the time domain structure analysis. It takes a very heavy effort and also times and computational effort. So that's why they selected a very selectively load case. They select the selective load case, and also even selected the load case, they selected a very short duration of the event to assess the structural analysis. And during this, there are some missing parts in the load cases. That's why we developed all the load component used in the ILA analysis, directly mapping to the structure model and then get a structural response. That's the main purpose. So currently, TRUST, originally it was started for just to generate the time domain structure analysis. Now it's evolved to the suit. Suit means that from the ILA analysis and load mapping and generate the time domain analysis and structural assessment and the structural optimization or modification spiral. So we are thinking about that kind of the suit, but that's all the component-wise development. So we can combine some component and we can do some selectively to the assessment. The main methodology is that the synthesize the load component and corresponding response component from fully coupled aero servo and less to hydrodynamic analysis tool like OpenFAST. And we can use a structural analysis software like Nastran, ANSYS, other conventional commercial software tool suite. And the main output is that the time series of the structural stress component at every location of the finite element model. And once we get this time series, we can apply to the class rule check program or the programs to assess the strength check and fatigue check and also the buckling check. This trust packages has been applied to the several FOWT projects. For example, in Korea, there's Grayware project and SCIP pre-feed project. And the KR is developing the time domain structural analysis guideline. When they developed that guideline, they applied this trust package to assess the structural response. And also Korean government funded the organization, CRISO. They want to develop the Korean specialized the FOWT model. At the time, they applied this trust the package to develop the pentasemi concept. And recently, the Hana Ocean, they are doing the pre-feed study for the some application FOWT. So they used this package to assess the structural assessment. The main feature is that this is quite fast and light. So compared to the conventional, the traditional time domain analysis, that means that the traditional time domain analysis, every time they synthesize the loading and the mapping to the finite element model and solve the structural response. And compared to that, it has at least 10 times, at least 100 times faster. And also, we are limited, we are very minimized the memory requirement. So the full-time analysis based on the conventional, traditional time domain analysis, it takes just 10,000 times less data storage. Because it is very fast, the synthesizing toolkit, so we don't need to save all the time history to the disk space, because that once you need this time history, you can run again. So within a couple of minutes, you can get all the time history. And these trust packages, they include all the ILA set. But in the ILA setup, definitely we need to validate some hydrodynamic coefficient. In this case, we applied the safety technology, FE wave. FE wave is the front end of this numerical wave basing based on the safety technology. the main server, we are using the Siemens StarCCL Plus. So using the HLS, high-level spectral method, we generate the extreme wave. Now we are coupling with the aerodyne and modyne, so we can solve that actual the FOWT model in floating FOWT model. And motion and structural loading can apply to the trust from this CFD model. So we can do the motion analysis in the CFD, the every wave packages, and also provide the structural loading to the trust. So with the CFD analysis, we can get a hull motion and bearing response, and also structural response can be obtained. As you know, that this CFD tool, there is no any missing part, so it has a quite, it can raise the fidelity of the design analysis. Especially the CFD is quite good application for the air gap and the wave impact simulation, since this package can provide the loading to the truss. So once the structural model is ready, you can obtain this impact load time history and also impact load time history. So this numerical Bayesian also applied to the previous project, the Gray Whale project in Korea, and recently Hanwha pre-feed study was applied. Usually this wave basin code is applied to get the hydrodynamic coefficient tuning, like the Morrison member and the motion response RIO, by tune this drag coefficient. And chrysopentasemide development definitely was applied and compared with the model test data. Yeah. Trust itself is synthesizing the ILA result and also the available structure model and generate the time series of the structure response. But during the project, there's some need to have some design spiral, because that once they complete the ILA analysis and corresponding structure response is obtained, they need to change the revise the structural model and then do the analysis again. This is a repeated the spiral. So we have some the pre and post process tool is developed. So from the hull design, it's like hull sizing stages and generate the ILA model, for example, OpenFAST or the input model, template model, and the neighbor architects. They tuned all the hydrodynamic coefficient utilizing the CFD analysis, and then to the analysis, and using this ILA result, the trust is applied to the ILA result with the FE model. Definitely, FE model is structure engineers developed this FE model, and then a time domain analysis is completed, and then structural assessment is done if there is a needed. So structure engineer modify the structural model and then do again this spiral. So the trust packages and tool suite is developed for the auto spiral, optimal spiral analysis. When we developed this trust tool, we are thinking about that. So this trust tool should be available in the PC level, because most of the engineers, they are using the PC, not HPC. So even though they can use the PC, but it does not take a long time. It does not take a heavy the computational power or the disk space. That's keep in mind. So eventually, these trust packages can be lightly run in the PC basis, Windows PC base, and the heavy run case, definitely we can apply the massive HPC system. This trust synthesizer is quite quick and the light system. So structure engineer, even labor architect and structure engineer quickly run and easily run these trust packages to get the time history of the structural response. for example, for heavy run, as you know, the floating offshore wind turbine cases, there are so many DLCs should be covered for the ULS and FLS cases. So this number of DLCs easily over the 5,000 cases. So if you're using the HPC environment, it can be done within 9 hours. This is revising right now. But anyway, the previously was 9 hours from the ILA. ILA means the OpenFAST run to the structural assessment, including the ULS and FLS. This is a one-ton structural assessment after structural engineer have some need for changing the structure, and then second run will also take 9 hours. So, and this trust package can be run in the PC because we apply the multi-threading routine in the trust packages. For example, the 40,000 element cases can be generated the time history of all the elements, structure element time history for 1 hour simulation in the RA. It only takes 10 minutes in the regular laptop pieces. But as you know, the structure engineer, sometimes they can do some screening purpose. They need to run the whole element synthesizing. But after they find some critical ranges, we don't need to synthesize the whole element system. So we can focusing on some critical elements. For example, floating offshore wind turbine cases, the critical point is that the connection from the substructure and the tower base or the pontoon corner and the top raised corners, there will be very limited number of the elements. In this case, it's very quick. So, for example, the 3,000 element selected element cases. So the 1 hour simulation, 1 hour time history to generate the 1 hour time history of the structure response, it takes 90 seconds. Even very focusing on the hotspot element, for example, 141 hotspot element, takes 15 seconds. Yeah. Because the trust dealing with the several programs like the ILA program and the structure analysis program, sometimes the hydrodynamic coefficient generating program like WAMI. So a little bit, it can be little bit complex. That's why we developed some integrated the data handler. We call it Trust Input Manager. So through this input trust input manager, it can automatically generate all the input file for the trust application. For example, the ILA input and the structural mapping input, that kind of things. And also we provide some the formalized folder structure. So the folder structure is named very intuitively. So the engineer can easily access the folder and then get some result. And this input manager provides several batch files. Batch file is numbered 1, 2, 3, 4, 5. So engineer just click the serially one batch file, second batch file, 3 batch file. So easy to execute. And also using this input manager, from hull sizing to the structural assessment, so it can be easily do some design spiral. So can be and also all this trust suite is coded by the multi-threading capability. So it can be run parallelly in the Windows system. Definitely the HPC system, we are doing some parallel analysis. So even though the ILA execution and also synthesizing all parallelly can be done. And from the structure modeling, we need to generate some hydrodynamic panel generation for hydrodynamic coefficient generation. It also it automatically Recently, we add up some pre-screening capability. So even though the engineer did the ILA level analysis without the actual structure analysis, using this ILA analysis, we can preliminarily estimate the structural fatigue. And then structure engineer, when they designed the structural model, so using this preliminary structural fatigue prediction, they can apply this design modification using this information. Definitely, the ILA data, they provide the mooring line tension variation. So this pre-screener, so read this all the mooring tension, and along the tension line, any kind of any point of the mooring tension, they can provide the strength, the utilization factor, and also fatigue damage or fatigue assessment. And these trust tools provide some statistics. So floating offshore wind turbine has lots of the design load cases. So huge the number of these design load cases done, and then we need to summarize all the result statistically. So trust packages provide this statistics summary table in terms of the CSV file format or HDF file format. So sometimes some DLC has a random seed variation for the same DLCs. In these cases, we provide each realization statistics and also summarized and the viable fitted or the compare fitted extreme statistics. After we get all the average the result for each DLCs, this trust package provided the graphical interface for the result in terms of the contour plot. For example, the structure model cases, all the element has a contour plot of the strength and also fatigue damages. And for each DLCs, for example, the fatigue damage cases, usually we handle the 300 to the 5,000 fatigue beams. In this case, we provide the dashboard. Dashboard is shown in the next slide. Using this dashboard, we can easily figure out the maximum or design criteria, also trend. How is the trend according to the environment condition cases. This is trust provided the dashboard. So dashboard summarized all the environment condition first, like wind speed, wind direction, and wave height, and wave direction, current direction, like this. And some key parameter index case, like acceleration at the nacelle, and some damage, the structural damage for the selected element, the kind of things. So in this slide, you can see the total more than 5,000 DLC cases. So how is the damage or acceleration varies according to the environment condition. And the extreme value is showing in the left-hand side as an indicator. So engineer can easily decide that this hull is satisfied the design criteria or not. For the fatigue state, this is fatigue state. So the last line shows that the accumulated fatigue damage curve, and along this curve, how the growth of the fatigue. And each beans, which bean shows that the extreme fatigue damages, so you can find it. This is the trend curve, and the right-hand side is a heat map. Heat map is the correlation graphs. A correlation like wind direction versus wind speed. Where is the maximum criteria happens? Or you can easily change the correlation, like wind direction versus wave direction, wind speed versus wave height. You can easily change this parameter, and then you can find this heat map result. So with these indicators, people, engineer can easily handle the very huge amount of the result from the ILA result and also structural result, structural assessment result. When we have applied this trust package to the previous project, but our client keep asking us that some further investment or further implementation. So one of them is that drag trust case, drag load mapping from safety analysis, because some of their client hull has the viscous dominated structure is there. So potential based ILA analysis. So loading estimation is some uncertainties. That's why they want to apply the CFD and directly this CFD result to the structure analysis and get the response. So that's why we are implementing that kind of load mapping. And the other one is that substructure, usually the rigid body assumption, but they want to apply that some dynamic structural response. So elastic substructure model and the corresponding structural analysis is also implementing. Numerical wave basin case, FE wave. So it is keep going on the full integration with the ILA model and also the structural assessment. So in this case, FE wave provide the nonlinear hydrodynamics to the structure model, and also aerodynamics controller and tower response and boarding response comes from the ILA model in terms for example the OpenFAST model. And this numerical based model, it can obtain the loading from the nonlinear wave and directly mapping to the structure. And then through the trust, we can gather some structural response for this nonlinear wave. That's ongoing and the near future implementation topics. Yeah, that's a quick introduction to the trust and FE wave and all these we call it trust packages. So is there any question? Then
maybe I just ask a question. So when you couple with CFD, you do the similar as you do with OpenFAST, but here you are calculating the motion of the floater inside the CFD.
Yeah, motion calculation from the CFD.
Yeah. But in the case when you couple with OpenFAST, it's OpenFAST who gives you the motion.
OpenFAST provides the aerodynamic loading.
No, here, okay, but in the case of potential flow solver, which is global performance in OpenFAST, they give you the loading and the motions. What I understood.
So in here, CFD is master.
CFD but I'm not talking about CFD in general. Here it's clear because you are calculating the motion and everything will be perfectly balanced and so. But when you use the OpenFAST, then you load your finite element model with both with the pressures and the motion, and this motion comes from OpenFAST.
Yes.
But there might be the misbalance of the inertia and the pressure loading.
No. When we do coupling OpenFAST and CFD, we use only part of the OpenFAST.
Yeah, I'm not talking about CFD. About the previous
OpenFAST TRUST.
OpenFAST
TRUST. Yes.
Oh, okay.
In that case, because you are calculating the motion, so you have correct inertia and everything, and implicitly everything will be balanced. But in the case of OpenFAST TRUST, you are receiving the motion and you apply the loading differently. So the balance between the inertia and the pressure loading.
So basically that's why whenever is OpenFAST or complex or even CFD, we try to follow almost not exact 100% or 99% same procedure as you do in ILA in structure. So for example, hydrodynamic, you have all these diffraction, element damping coefficients, right? So then we actually use pressure distribution with the same software, which if it integrates, it is going to be hydrodynamic coefficients. But we have the same distribution in the trust.
Yes.
And the inertia, we actually, before with ILA, we actually compare FE model mass elements, sum together, whether it matches with the 6-0 freedom.
I fully understand
matrix. Yes.
But inertial loading, I mean, the acceleration coming from the OpenFAST,
Right.
you apply them directly in your finite element model.
Right.
But the pressure loading, you have some interpolation and something. So you will have some something to adjust to be balanced, if you see what I mean.
Interpolation, but we use the same WAMI, same panel for the.
I understand.
Right.
Okay. Maybe we can okay. Because the integration is not performed in same way. When you apply it to the finite element, you have finite element nodes or elements. When you have WAMIT, you have panels which are not the same. So you need to interpolate it. And when you are interpolating, you lose something.
Okay,
we have similar problems.
Because that's why you mean that the hydro panel and the
finite element
are
not the same.
So it's not same. So that's why we apply the WAMIT functional. WAMIT, we apply the finite element weighted point directly to the WAMIT. Inside the WAMIT, they computed all the point pressure directly, and then we map into the structure as it is.
Okay.
So
that can
actually regarding load balance, maybe interpolating hydrodynamic panel may be better because it has the same distribution, right? Resultant.
Whatever you do, I mean, you can do both ways, but
right.
you need some adjustment at the end, like inertia relief or something. Otherwise, you will.
So far, look like that's why there could be some minor unbalance, right?
Yeah. That's what I'm talking.
So we have some sort of the empirical trick.
Yeah. Okay.
Yeah, like where to put all the springs.
Yes.
So they kind of whatever unbalance force.
It will be there.
Just show up in a fairly or whatever.
Okay. Yeah, you are aware.
I know you are expert of that.
No, but we just need to be careful. But I understand what you are doing.
Because you taught us how balance is important in your homework, right?
Yes.
So,
but here is clear because you are calculating the loading and transferring the motion. So it will be balanced.
That's true. Yes.
Thank you. But I think you are doing well.
Thank you.
Good.
Okay. Then
maybe
any other questions online before we jump into the work packages? Okay.
Work package 1.
And you want me to go through these slides?
you are the PI.
Well, there's some things in here that may be best for you, but so yes, work package 1 as Jane summarized earlier. I think that the first thing is making sure that this interface between OpenFAST and TRUST is fully compliant and maintained going forward. So we want to formalize the interface between OpenFAST and TRUST, meaning all the data that TRUST need to do its solve, tower base loads, Fairlead loads, all the motions across the finite element model of OpenFAST need to be sent to TRUST in an efficient way, and just making sure that thing is robust and supported. Jane also talked about the making sure that this thing is reusable, and so we want to make sure that the test cases we develop here get imported into our regression test suite, so that when we do a next release of OpenFAST, all these things are checked in the approach. So that's all part of this work package 1. First of all, on the software side, is making sure that this interface is fully compatible and maintained going forward. The second thing is maybe some trust things. Maybe you want to talk about those, Jane. your KPIs and so on.
Right. Actually, we like to actually hand over some part of the post-processing tools to NREL. That way, we have a consistent post-processing from OpenFAST TRUST. So there will be the part of software development.
Yeah. So again, all the key things will be maintained on the active side there. Next slide. Second part of this is on training, and I think there's a couple layers here. We want to make sure this thing is usable by the community, and so a lot of our past OpenFAST training has been very much high level, and this is trying to get down into details. If you're really trying to do an integrated loads analysis following an IAC, you need to set up the various modules. We need to set up the FEA model and couple them together. This is really a combined training of that whole package. We intend to do both some in-person meetings in this JIP and also do YouTube recordings so that we have that going forward for new engineers. Yes. Yeah, and the schedule we're proposing, obviously we can iterate here, but assuming it all works out as planned, we would start in 2025, and the first year would really be completing this interface on the software side and doing release. We'd have the training towards the end of the year on the first year, and the second year, this is heavily towards the first year, but the second year we want to, of course, absorb any feedback that the community has, and release an update, and then do a second training workshop at the end of the project. And there's our budget. NREL's the PI on this side, but there's some work on Fund Energy side. There's the rough budget we're estimating for this work package.
Okay, this work package. Any questions?
Any questions on work package 1?
No.
I have a question. What will be the validation or the validation processing, and when will that come out?
Yeah, that's part of work package 2, and there's also some tie into OC7. So hold that question, and hopefully we'll answer it in the next few slides.
Great, thank you.
Actually, work package 3. Right.
Nevertheless, it's coming. Thanks for the question, Jerica. Anyone else on work package 1? Hopefully it's pretty clear based on what we've discussed so far.
Okay. So yeah, next one is that work package 2. This is an industrial application of the OpenFAST and TRUST. So this work package 2 targeted the pre-FEED level affordability design development. So we selected some wind turbine and oil types and wind farm site from the participant, and we'll do the initial design by sizing and scheduling. And the initial design cases, for the initial design cases, we developed the OpenFAST and TRUST modeling, and we'll perform the ILA and time domain structural assessment at the initial design. So this ILA and time domain structural assessment covered at the ULS and FLS. ULS cases definitely DRC 1.6 and 6.1 parking condition, and DRC 5.1 shutdown cases will be covered. And yeah, particle assessment to definitely 1.26.4. And ILA and the structural assessment to look for the design refinement according to this assessment. If there is some need for the design update for structural model, then we can look that the design is viable. As a deliverables, we'll develop the design basis and the whole design and analysis result, and definitely assessment report will be issued. And also the OpenFAST and the TRUST model of the final design will be shared.
Just to be clear, I think we're proposing here to use the IEA 15 megawatt as a reference turbine for this floater.
Okay. So schedule-wise, first 2 years, we'll develop the initial design, and we'll do some design refinement, doing the ILA analysis. And also we'll provide the training workshop during the biannual progress meetings. And second year, we'll do the structural assessment with update to the OpenFAST and TRUST packages. And definitely we'll provide the training workshop. Okay. Yeah, is there any question about the work package 2?
You can also, one thing based on some feedback from industry, so this is also the setting track record for OpenFAST and TRUST. We try to get the approval in principle from class. So we didn't decide who, maybe BV. So yeah,
maybe ABS too.
ABS, yes, or DMB. I don't know whether they like. Okay, so so we estimated AIP cost, but this is still estimation. So we consult with ABS and BB, and potentially some other classes to clarify this cost.
The structural design will be made by whom?
It will be made by original configuration. We have some survey. So once configuration is done, the actual design will be by the NL and front energy, the joint team.
Yeah, I understand, but
the detail of the scaling.
Scaling, yeah.
Scaling, the most likely front energies will take care of.
Okay. Because your finite element model at the end should include everything.
Yes.
Related to structure. Yeah.
Okay. Structure, the ballast way, and the equipment, some details. Yeah. So this is we are not trying to make new design, but it's more like make a good example for the industry people, especially the young and starting companies who can follow step by step. So we'll try to offer as much as possible, starting from the scattering check, sizing sheet, all those things. Yeah. So this is more like training material, but all the design at least should go through the industry standard procedure. Hopefully, carrying some AIP too. Yeah. Okay. Any questions? Okay, then.
Okay,
Let's go to
package 3. Lou?
Lou, are you there?
Hi, yeah, I'm here. So should I take over screen sharing for the next couple slides, or maybe you can control it?
Yeah, why don't we just say next slide, Lou? I think that may be the easiest.
Okay, so again, just control it. All right, so yeah, let's talk about Work Package 3. So Work Package 3 is focused on developing hydrodynamic CFD simulations coupled to the various modules of OpenFAST. So in this proposed framework, the hydrodynamics module of OpenFAST will be essentially replaced by high-fidelity CFD simulations, while the other modules of OpenFAST will model the loads from mooring, aerodynamics, structural dynamics, and control. So the motivation for this work package is really twofold. So first of all, based on our experience over the past few years, we found the modeling and calibration of hydrodynamic loads on a floating platform remain a significant challenge in mid-fidelity tools like OpenFAST. So this is in part because of the wide variety of different platform designs still being. Oh, sorry. Can you go back to the previous slide?
This one. Yeah.
Yeah. So I mean, still, we have still a wide variety of platform designs being considered. So this is in some contrast to the aerodynamic modeling with mostly converged rotor and blade designs. So we also, sort of some of our research observed very high sensitivity with the tuned hydrodynamic coefficients, such as drag coefficients. to different platform geometries and sea states. So this sensitivity poses further challenges to model calibration. So I think in this respect, high fidelity CFD simulations has an important role to play in providing reliable reference floater response under realistic conditions for the tuning and validation of mid-fidelity hydro models. So the second motivation comes from the fact that certain highly, I'm not sure why I keep moving to the next slide. Yeah. So okay. Anyway, so yes, the second motivation, comes from the fact that certain highly nonlinear hydrodynamic loads are very difficult to estimate in mid-fidelity tools, such as wave impact loads from breaking waves and slamming loads. So definitely some progress is being made in the mid-fidelity side to predict this type of loads, but I think CFD still has a very important role, both in terms of providing validation for mid-fidelity models, but also in terms of directly predicting the critical extreme loads on the structure. And of course, I think we already discussed that CFD also has the advantage when it comes to more straightforward and exact load mapping of extreme events to structural modeling tools such as TRUST. But with mid-fidelity tools, even if we can predict the global extreme loads using some sort of semi-empirical modeling, the load mapping to structural solver will still be a major problem and will inevitably rely on some assumptions about the load distribution. So I think that's basically the rationale behind this work package. So now we can maybe go over the proposed work in a bit more detail. So work package 3 is divided into. Can we go back to the previous slide? Yeah. So yeah. So yeah, so work package 3 is really divided into two parts. So the first part is on the necessary code development for coupling the various modules of OpenFAST to a CFD solver, as both front energies and NREL are using StarCCM+. So the key couplings listed here are between the Elastodyne and Moordyne modules of OpenFAST with StarCCM+. So Elastodyne is the main dynamics solver of OpenFAST, responsible for solving the rigid body motion of the floating platform, the bending of the tower and blades, and also the dynamic of the drivetrain, the dynamics of the yaw drive, etc. And Moordyne is the dynamic lumped mass mooring solver of OpenFAST. So these two modules will be independently coupled to StarCCM+. And the current plan, I think, is to use StarCCM+ to solve the hydrodynamic loads on the floating support, as well as the rigid body motion of the platform. The reaction load from Elastodyne, the tower base, and Moordyne will be the inputs to the CFD solver, and the CFD solver will output the platform motion back to the OpenFAST modules. So I think Moordyne already operates in this fashion, taking the fairly motion as input and returning mooring reaction loads, but some modification to Elastodyne will be required. So currently Elastodyne operates in the opposite way. It takes the hydrodynamic and mooring loads, some at the tower base as input, and output the tower base motion. So we need to essentially flip this and include a secondary mode of operation in Elastodyne with the input and output reversed to support coupling with CFD. So this kind of falls under this first part of the work package. Also, I think not explicitly stated here is the inclusion of the aerodynamic module, the servo control module, and also the dynamic inflow wind capabilities of OpenFAST in the couple simulations. So all these modules only communicate with Elastodyne and not directly with the CFD solver, based on my understanding. So they're not listed here. So the linking between Elastodyne and the rest of the OpenFAST modules are covered by the glue code development listed here as the second bullet point. So as part of the deliverables for work package 3, we will provide the JIP participants with coupled modules and coupling codes developed along with a report on how to set up the simulations. We also plan to have extended support for the coupling with future release of OpenFAST. My current understanding is that Front Energies will handle the CFD side and NREL will support the OpenFAST side, but I think the details can be discussed in the future. So can we move on to the next slide?
Finally.
Yeah, sorry. Okay, yeah. So, well, the second part of work package 3 is focused on running coupled OpenFAST CFD simulations to help calibrate or tune mid-fidelity hydrodynamic models in the Hydrodyne module of OpenFAST, and also validate OpenFAST only simulation results. So this exercise will be, performed using, I think, the floater design developed in Work Package 2, discussed just now, for selected load cases from the integrated load analysis. So through this exercise, we will also develop the, the relevant recommended model calibration procedures as part of the deliverables. So as shown on this slide, I think the planned work can be roughly divided into 2 steps. So first, we will conduct CFD simulations coupled to the mooring solver only. So we will run a suite of load cases, including free case simulations, regular and irregular waves, and also combined current wave conditions. So the regular wave CFD simulations will use Front Energy's FE waves tool introduced just a moment ago. So the results from these hydro-focused, coupled CFD simulations will be used to calibrate a mid-fidelity hydrodynamic model in the hydrodynamic module of OpenFAST for different sea states. So in the second step, we will conduct more complicated coupled OpenFAST CFD simulations for several load cases with tower and blade flexibilities, aerodynamics, controller excellence, etc. So this results will be compared to those from the equivalent OpenFAST only simulations with the hydrodynamic model tuned in the previous step. So this comparison really serves 2 purposes. So on one hand, it helps validate our model tuning procedure and the calibration procedure developed in the first part. And also it serves to verify our implementation of OpenFAST CFD coupling. So I think we'll also take this opportunity to investigate and estimate quantities that are not easily obtained from mid-fidelity tools like OpenFAST alone, such as air gap and wave impact loads. So yeah, next slide. All right, so this is a rough schedule for Work Package 3. So the first year of the JIP will be spent on the necessary code development and some preliminary verification. We will also develop the necessary documentation on how to set up the coupled simulations in year 1. So the second year of the JIP will, essentially apply the tools developed to perform coupled OpenFAST CFD simulations to help develop the methodologies to calibrate mid-fidelity hydrodynamic models in OpenFAST and also validate the OpenFAST RLA predictions and OpenFAST CFD coupling. So yeah, I think in terms of deliverable, we'll do a report on the calibration procedure for the mid-fidelity hydro models. And also probably prepare a verification and validation report. And training workshops are planned during biannual progress meetings in the second year. So I think this pretty much sums up the proposed Work Package 3 of the JIP. I think we can open up to questions.
I have a question on just additional validation. So it's great that you're validating OpenFAST to CFD, but are you going to also validate between the hydrodynamics of the, sorry, someone ring my bell. 1 second. So is there going to be validation between the hydrodynamics that's going to be calculated in TRUST and OpenFAST, also compared with the CFD? And then is there the validation with the structural model of TRUST compared with a comparable solver like ANSYS, for example?
Right. So Work Package 3 is really focused on the hydrodynamics only, not so much the structural dynamics. So TRUST doesn't really play a significant role in Work Package 3. So I think in the upcoming slides, we do have some OC7 verification study that will involve code-to-code verification of TRUST results. But not so much here in Work Package 3, like I said, which is mostly focused on the hydro side.
Yeah, the verification of the structural solve, there's actually an open forum already through the IEA Win Task 56, and we will talk about it next. We don't need to, crowdsource funding for that one because we already have it laid out.
Okay, so it's just another, the IAA task force is going to cover the structural validation, correct?
Right. That's right.
And this is only looking at, but there is in the TRUST analysis, if I understood correctly, there is an aspect of calculating, you know, some of the hydrodynamics in trust. Correct? Like the Willamette potential theory coefficients for
Yes.
each of the panel methods. So is that going to be a part of this work package 3 where it's, you know, you're checking, you know, what's solved in trust is checked to OpenFAST is checked to the CFD?
I would treat them as two like, so the whole integrated loads to structural analysis, including hydrodynamic loads, you know, not CFD based, but potential flow strip theory will be covered under OC7. And then I would say that the sort of the FE wave CFD solution has already been quite validated. And work package 3 is really about checking the coupling to OpenFAST and making sure that we believe that that's robust. That makes sense.
See, yeah, we can share some of the validation related to the CFD side from the previous project to the participant.
But the direct, CFD to trust is not yet being proposed in the scope.
Okay, thank you.
Mm-hmm.
I have a question about FE wave. Is it a CFD solver or is it a tool to couple star CCM with other solvers? That I didn't understand. Is FE wave inherently a CFD solver, like based on finite volume or?
Actually, FE wave originally developed as a glue code for some nonlinear wave model and other mooring like Moore die. But then later it just focused on with the stars. Basically, CFD solver, we just use either open source or commercial CFD source. This is more on interface, but it includes the fully nonlinear wave model, which generate both regular and irregular fully nonlinear waves that can be used as input for the CFD. So that is part of the
my interpretation, and correct me if I'm wrong, but this is my understanding, because I had the same question a while back, was that, you know, star CCM or the CFD solvers do really well for that wave body interaction, but they're very, very expensive to do that for irregular sea state. So what FE wave allows you to do is basically combine that CFD solution near body with the potential flow far body. And that's not a feature you can get directly in star CCM, but that's basically what FEA provides, is that extension to, you know, near body CFD, far body potential flow. Correct me if I'm wrong, but that's my understanding.
Yes,
Okay.
you nailed it.
Okay.
And can we replace star CCM with OpenFOAM and use it for free?
Yeah, actually, we have an interface, but the problem is the guy who developed went to the IT company, so I can ask him.
Okay.
But we had actually the part of this supported by the CRISO, so we delivered to them. The only problem is now we don't use much, but if someone has a special request, we'll find a way. Yeah.
Okay.
And as I mentioned earlier, NRELS also has a lot of work in high fidelity modeling. And I also imagine at some point we may want to couple the FE wave capability into the NREL.
Maybe the better way would be, actually, we plan to handle all the FE wave source code to the NREL. So you can ask NREL.
So FE wave will become open source, you're saying?
Oh, yeah. Yeah, we don't have the step to keep developing, so yeah.
But unlike FE wave, Trust is an inherent FEA solver. It can do the structural analysis itself without depending on other solver at the moment, right?
You need you can use any FEA structure solver, but you need to have one. We are not providing actual solver. You can use ANSYS, Nastran, whatever, or Excelos, the whatever tools available outside. So, but
Okay.
as far as you actually, that's part of the some OpenFAST, the trust side development. We'll make some neutral data format. The FEA model, the software can generate. So but you still need your own FE solver. Yeah.
Yeah, and again, just like FE Wave, Trust is like that interface. OpenFAST and does all this mapping for you in an efficient way. So yeah, you can, if you use ANSYS or Abacus or Nastran or whatever, you still have to use that solver. Trust just makes that process quite efficient.
Okay, I see. Thanks.
Trust is kind of loading mode, finite element loading mode.
Yes.
Loading
of finite
Loading,
element. Yeah.
loading and
But
and
finite
something-
element
and
gives
something.
something. Yeah.
It's that magic glue.
Anybody can do that. So, but
Yeah.
we just did
I think
Some people say it's like Columbus egg.
But yeah, it doesn't avoid you having your own FEA license. So.
Okay. And
Okay.
OC7, yeah.
All right, yeah, so yeah, I don't know if this topic is of interest to people online, but yeah, when we first started developing the JIP, we did receive some requests to clarify the differences between the OC7 project and the proposed JIP. So the two projects are funded separately. So you know, in case you're not familiar with the OC projects, OC7 is a verification and validation project. Run under the International Energy Agency IEA Wind Technology Collaboration Program Task 56. So this is a large collaboration project led by NREL with I think about 24 participating organizations so far, you know, across the globe. So it primarily focuses on the development, verification, and validation of mid-fidelity engineering tools. Of course, an example would be NREL's OpenFAST. So the OC7 program at the proposed JIP has some very important alignments on several topics. So I think we can take this opportunity to you know, highlight the potential synergies between the two, and also more importantly to clearly delineate the scopes of the work between the two projects. Next slide, please. All right, so just first some background information. So the current ongoing OC7 project is a continuation of several past OC projects, starting with the offshore code comparison collaboration OC3 project back in 2010, I think. So the series of OC projects started from, you know, code-to-code verification of mid-fidelity tools up to, you know, validation against wave basin or full-scale data added in, I think, in OC5. So the more recent OC projects, such as OC6 from 2019 to 2023, and the current ongoing OC7 project started to focus more on specific phenomena, while still remaining at its core a collaborative VMV project. So the current OC7 project just kicked off at the beginning of this year. So this slide shows the three primary phases of the planned OC7, and currently we're about a quarter of the way through phase one, so which is focused on examining and improving how we model hydrodynamic viscous loads in mid-fidelity tools. So phase two, starting in 2025, will focus on structural loads and, you know, primarily focusing on the validation of global structural loads, such as member level moments and stress from hydroelastic simulations against wave basin experiments. But there will also be a component on code-to-code verification of global to local load mapping for detailed structural design analysis. So basically what TRUST is doing. So the final phase is not as relevant. So the final phase is on aerodynamic modeling of floating wind farms. So most of the alignment is basically between the first two phases of OC7 and the proposed JIP. Next slide. All right, so I think this slide shows the list of SAP tasks within each phase of OC7. So focusing on phase 1 and 2, or work package 1 and 2 here. So we have a list of subtasks in the red box that are most closely aligned with the OpenFAST-TRUST JIP. So in work package 1 on hydrodynamic viscous loads, we have work package 1.1 on the validation of engineering hydrodynamic models for a variety of designs. We have work package 1.2 on developing recommended practices for hydrodynamic modeling, and also finally work package 1.3 on some hydro-focused CFD simulations. So in work package 2, we have 2.1, so on the validation of member level loads from engineering hydroelastic models, and also 2.2 on the one-way global to local load mapping for structure analysis. So I think in the following slide, I'll go over some of these work packages to highlight potential synergies between the two projects, and also kind of try to delineate the scope between the two separately funded projects. So next slide, please. All right, so yeah, as I've mentioned, so the OC project at its core is a validation project using experimental data. So even though we're focusing on specific phenomenon, so in work package 1.1, we're trying to improve the modeling of hydrodynamic viscous loads on offshore wind platforms, with the help of 3 weight-based experimental data sets. So from left to right, we have an experimental campaign focusing on the nonlinear wave loads on a fixed structure. So using this data set, we're investigating the contribution of viscous loads as a source of nonlinear excitation that potentially excites the low frequency resonance motion of a floating wind platform. So as shown in the bottom left, we're investigating how the viscous load modeling is affected by a variety of different model configurations. The geometry studied here is mostly inspired by the deep sea wind. So I think we're currently wrapping up this investigation, and through this work, we have verified the effectiveness of some modeling techniques, such as wave stretching with strip theory or Morrison drag force, and also a modified form of the heat plate drag force that really improved our ability to capture the low frequency viscous excitation. So we also investigated how the relevant drag coefficients change with the model configuration and with the sea state to hopefully guide future model development. So in the middle and on the right, we have 2 additional data sets. So we have the Windmore data provided by Syntef Ocean in the middle, and also a data set derived from the focal project that is based on the Volturnus S reference MS submersible developed by NREL and UMaine. So in these cases, the structure is floating, and we'll be investigating what is the best model formulation to capture the floating response, especially the low frequency resonance motion of these 2 different semis. So in particular, both of these designs feature rectangular pontoons not investigated in prior OC projects. So we're dedicating additional resources in the form of CFD simulations to study the viscous loads on the rectangular pontoons. So we only just started working with the Windmore platform in April, and we'll start with the Volturnus data set later in October, I think. Next slide. Right, so this slide summarizes the ongoing and planned CFD simulations under OC7 Work Package 1.3. So as I've mentioned, we're primarily interested in understanding the viscous loads on the rectangular pontoons. So we want to understand how the pontoon drag coefficient change with various parameters. So we decided to simulate a suite of simplified scenarios using CFD. So we first started with the simple 2.5D simulations of an isolated pontoon without free surface, undergoing forced oscillation at different frequencies and amplitudes to basically understand the dependence of the drag coefficient on the Casey number and also the Reynolds number. And currently, we're simulating the 3D Volturnus platform with free surface on the right to investigate how the complete platform geometry influences the hydrodynamic coefficients. So basically how the coefficient varies along the pontoons and how the free surface influences the coefficients. So again, we're mostly focusing on simplified scenarios such as forced oscillation for decay and structure in regular waves to kind of investigate the fundamental behavior of the viscous load on the pontoons. So we are also separating the structure into many different parts, as shown by the different colors in the sketch on the right, to kind of investigate the local viscous loads on different parts of the structure. So we hope the the insight gained from this CFD study can provide further hints on how to set up our mid-fidelity hydro model in general. So next slide. All right, sorry for the wall text, but I'll try to summarize a little bit. So this slide basically summarize the key objectives of the OC7 phase 1 investigation and how it aligns and differs from the proposed JIP. So in particular, work package 3 of the JIP on calibrating OpenFAST hydrodynamic models using coupled CFD simulations. So as I guess I've already discussed, so OC7 phase 1 is primarily focused on developing and validating improved mathematical model formulation for the hydrodynamic viscous loads. And through this exercise, we're also working toward identifying a critical set of drag coefficients that will require tuning, and also investigate the sensitivity of these critical coefficients to geometry and sea state. So the CFD investigation OC7 is really designed to directly support this effort by investigating the fundamental behavior of local hydrodynamic loads, especially the loads on rectangular pontoons, through simulations of idealized scenarios. So with the OpenFAST TRUST JIP Work Package 3, our hope is that we can directly leverage the findings from OC7, primarily in terms of using the recommended hydrodynamic model formulation developed in OC7, and also devise suitable CFD simulations to help calibrate the key hydro coefficients identified in OC7. There's also important distinctions between the CFD work in the OpenFAST TRUST JIP in comparison to the OC7 work. So the OC7 CFD work is in some sense more research-oriented by focusing on the more fundamental aspects of the viscous loads in idealized scenarios to guide model setup. But in contrast, the coupled OpenFAST CFD simulation, the JIP, is more application-oriented with a focus on fine-tuning and validating the mid-fidelity hydro model for specific designs directly to IOA cases with realistic wind, wave, and current conditions. Next slide. So, all right. So yeah, just finally, just jumping ahead, we also have very close alignment between OC7 Work Package 2.2 planned for next year, and also the OpenFAST TRUST JIP. So both are focused on mapping the global loads from integrated load analysis to detailed FEA models for structural analysis. But we do have very clear delineation of the scope in this case. So the OpenFAST TRUST JIP will basically fund the tool development site, including developing a formal interface between OpenFAST and TRUST with any relevant post-processing tools to kind of interpret and analyze the OpenFAST TRUST results. It also covers development of training materials on how to effectively make use of the coupled tools, and also develop an example analysis with a more realistic detailed structural design to be developed within the JIP for the participants as part of Work Package 2. Now, on the OC7 side, which is funded separately, we will develop the OpenFAST and TRUST models for some open source simplified design, not necessarily realistic, and run the relevant simulations to participate in the collaborative verification study. So we will compare the results from the coupled OpenFAST TRUST tool to the results from other OC7 participants, presumably generated using different tools for a code-to-code verification. So yeah, in the short version is that the JIP will cover tool development and OC7 will cover tool verification. So I think that's my last slide, and hopefully I've managed to kind of clarify the relation between OC7 and OpenFAST TRUST JIP. So I think we can pause a second for questions here.
Okay. Thank you, Lou.
I have a few questions, Lou. If you can go slide 39. Yeah, this about the wording, using the things like flexibility, structural dynamics, elasticity. I think it's used in a wrong way, because this case you are showing in the middle It's pure rigid body case. There is no flexibility. You are just measuring the internal loads. You are not scaling the flexibility, elasticity of the structure to real elasticity. It's just pure rigid body case. And your load cells, they will measure something. They will measure internal loads, but they should be made rigid, actually, as rigid as possible to measure, to not influence the flexible response in a sense. So this wording, I'm not very happy. I already said during one meeting, but okay. And then in the next slide, when you call the work package 2 floater structural dynamics, this is completely not correct, because there is no structural dynamics in this. This is only quasi-static structural response. And what you are doing in TRUST is pure quasi-static response. There is no structural dynamics. There is no vibrations. You see,
so that's
very important to make clear distinction.
That's not entirely true. If you don't mind me saying so. So in Work Package 2.1, that's a hydroelastic simulation. There is in fact structural flexibility in both the model scale experimental campaign and also in how we model this. So in 2.1, which is essentially the main package of WP2. So that's really focused on validating the subdyne model of OpenFAST.
Yes.
And it is not quasi-static. There is actually flexibility, not just in the load cells, but also the pontoon is flexible to an extent as well, and that's also characterized in the investigation.
I understand, but there is, in any case, there is no structural dynamics. And when you say flexible, it is flexible from structural point of view, but from dynamic point of view, it is rigid.
I think that's representing where we are at tank testing of flexible bodies. But we actually have a series of potential solutions. Work Package 2 is not fully defined yet. We have the one that's likely going to happen is that one where it's, like you said, it's basically a couple of rigid bodies protected by springs. So it's not a full hydroelastic member. But there's also been other experiments proposed, like at DHI, they did a full flexible spar, where it is like a beam element that is flexing the body. So we have different options, but we still need to finalize the choice.
I think you should not try to measure flexible. You see, you should try to measure the loading, because because you can apply the same loading on the flexible or rigid. You will have the same. You will not have the same internal loads. It's about internal loads. It's not about the structural dynamics. If you want to correctly measure, model the structural dynamics, that's because you would like to see the correct natural modes at those frequencies. But everything is so rigid that it will not be excited. But you want to, the goal is to measure the internal loads. That's the goal, not really about flexibility or structural dynamics. I think there is some misunderstanding here. And you cannot measure internal. You can measure internal loads in this case of this platform because it is isostatic, because you do not have structural members. But if you have a non-isostatic structure, which is most of the time the case, then you should make it fully elastic. But it's not very wise to make it fully elastic because it's very complicated. It's enough to measure the loading, and then from the loading, you can calculate internal loads for any type of elasticity. So these are kind of, I don't like the wording. I mean, it's not about flexibility or structural dynamics. It's about the loading. Yes. Because from a dynamic point of view, everything is rigid. But from structural point of view, everything is flexible. There is no rigid from structural point of view body. And basically what you are doing, Jiangwan, is you are calculating this quasi-static structural response, which means internal loads. From structural response, you deduce them from the structural response, and we would like to measure them dynamically. And they are, there are some. I'm sorry to insist, but I think there are some things to clarify regarding this the wording, structural response, structural dynamics, flexibility, or whatever, internal loads. Anyway, but I think that the model test which will be done in OC7 will be very useful regarding the internal loads, whatever, however we call them.
And then regarding the trust about whether this is quasi-static, actually the only reason we is a quasi-static is in ILA, hull is treated as rigid.
Yeah.
But then actually in the OpenFAST coming version, so there will be some flexible internal dynamics.
I do not fully.
So whatever, if you ILA consider structural dynamics, we still solve quasi-statically because
yes.
everything on the left side, we just have stiffness matrix.
Yes.
On the right-hand side,
It's dynamic loading. Loading is dynamic.
Right.
But it's not structural response is not dynamic.
Yeah,
loading is dynamic.
When you have a dynamic structural response, the only difference is inertia has a structural inertia, right?
Yeah. Models, which is big difference.
Right.
Big difference from computation.
I know. So when you properly solve the dynamics, so we in TRUST, what you do is we take this additional inertia component from dynamics.
I see, but I do not think you should look for the structural dynamics because everything is quasi-static. It's like for the ship, you know, it's like any semi-submersible.
Well, there's definitely a lot of floater designs coming down the pipeline that do have eigenmodes in the wave rate region. And
pipelines. Yes, pipelines, yes, but not the braces or pontoons. They're so stiff. They are so stiff. They are.
I'm saying some of the floaters coming down do have flexible modes.
Yeah, but not this one. Not this one, and not majority of them.
It's fair, but there certainly are some that have modes that can be excited by the wind turbine and by the waves and by the moorings, and so. This is our. There's definitely a need for more testing of things. But
I agree with you, Jason. But this is not the case for most of the platform we are talking about. And my first question when I ask about these natural modes of the tower, do you do it fully flexible or not? That's because we are looking for the natural frequency of the tower, which are far from the wave frequencies. So it's just to have those natural frequencies. I mean, what you are doing, I think, is good with the trust, because that's what we should do. I'm just complaining about the wording. The wording is not correct. And it confused the people, flexibility, structural dynamics. There is no structural dynamics in what you are doing, and you should not include it, because there is no dynamic amplification, because structure is so stiff compared to the wave frequencies. So that's okay.
Okay,
I'm sure we will talk again.
It's just our first meeting.
Do not misunderstood me. What you are doing is good. Just wording is not good, in my opinion.
Here's a word.
And also, there are actually I think some discussion in even actual project phase whether this the hydroelasticity should be considered, some of the tower modes, and some actual project they do. So it's in any case it's coming. So we actually it's good. We have a CMake here. You are quite experienced on that side.
This is not very much different from a ship, you know. Springing and dipping of ship, it's the same methodologies, but we are just using incorrect wording, in my opinion.
Okay. Noted.
Because floater structural dynamics, this is really not
I think
good
the floater is the problem. I think I agree that floater itself does not really have dynamics. It's rigid.
But I mean, the loading is dynamic. That's no problem. But loading is dynamic, but the structural response is quite static.
We don't need to iterate, but I agree.
I think we should. But if you will have, we have recently some projects for very huge 20 megawatt with the floater, then you need to consider both the floater fully flexible and include the added mass for the deformation mode shapes and the tower flexible. But that's a different story. Then you have structural dynamics.
That's what
we can do. I think this is our first foray to try to validate that we can do that without having great data.
I agree, but this is nothing to have about hydroelasticity. That's my point.
No, it's
okay.
Fair
you may change
So all right, I'll pass on the feedback to update OC7 materials. So
We need a beer.
Yeah.
Oh.
Coming soon. Coming soon.
So yeah, the next section is demonstration.
Any other comments on
Is
that? I
there-
think this is where we had a break, right?
Yeah,
we need a break.
So-
So we supposed to have a 15-minute break. So yeah, we are a little behind schedule.
Any other questions
Okay,
before? I
it's
think this
okay.
this last section is like optional for those who want to stay for it. But any more questions on the work plan, or I don't know about next steps? I think it's also a good time to kind of ask about next steps. We'd love to get feedback on what we're planning. Again, that we plan to have additional meetings. I know this time was very convenient for some Europeans. I'm very impressed that some people are still on Naki and so on. Salur and Victor, thank you for staying late. But we do plan to have additional sessions that are other times for Europeans and so on. But we'd love to kind of start pausing and getting feedback on the plan, and we're simply open to change scope if that's needed, and also expressions of interest of what if you like what you're seeing, or if you're thinking positive or negative things, we'd love to hear that feedback. So don't have to do it now, but yeah, just making sure that we open that up for the group to follow up on. Any final questions? Maybe we should take a brief break and have the demonstration.
Yeah, maybe 5 minutes.
Starting
Cigarette break.
Cigarette break.
4:10. Okay.
Okay, 15 minutes.
And then you come here. Actually, then Jason, I have some meeting with the other things.
I will be here. Okay. Just do as at home.
Okay, thanks everyone. For those who want to see the demonstration, you can stay, come back, just under 15 minutes.
So I prepared some slides to show that the same summary. So this demonstration covered that kind of the items, but first of all, the trust suite for the overall design procedure, how we apply the trust suite for design spiral, and in a little bit detail for the trust work progress, how we step by step go proceed for the trust application. And finally, we prepared some demonstration material, actual execution in the PC level. So this trust demonstration package covered the generic semi-submersible FOWT model with the 15 megawatt IEA wind turbine model. This is OpenFAST. So I will show that the one step by step how we do the trust application. First of all, so we started from the hull configuration. Hull configuration means that we need to do some hull sizing from scratch. We specify the hull dimension and the volume estimation and weight distribution in terms of the 6 UF motion. And we need to set up the hull turbine, the 15 megawatt or the 18 megawatt, whatever the required turbine. Turbine setup, we need to aerodynamic modeling, turbine modeling, and the tower model is definitely we need to set up in the ILA model. And also, according to the installation site, we need to design the mooring configuration. Definitely, we need some mid-ocean data during the hull configuration stages. And once the hull configuration is ready, we need to prepare the ILA setup. For this demonstration, we are using the OpenFAST. So otherwise, the other people can use the OCAPLEX also. So OpenFAST, we need to set up the hydrodynamic coefficient. This coefficient is coming from WAMIT. And also some Morrison member should be validated with the model test, but model test is now available, we can use a CFD model. And once the model is generated, and we need to do some system identification, so model setup checkup, and also according to the project requirement, so vendor can be provided some turbine performance data or the basic performance information. We need to check this turbine performance, the performance model in the ILA model. So this all kind of the things is preparing stages for ILA model. So once ILA model is set up, then we can put this ILA template in the trust package folder, and with this provide the MedOcean data. So we set up the load case file, including that wind speed, wind direction, wave information, current information, and number of random seed number. And the misalignment cases, we have specified the U angle. And for specific purpose, the wind data, we can put some specific number for the wind information, like turbulence intensity and the power law, that kind of things. And the next thing is that meanwhile the ILA setup, so structure engineer preparing the structure model, and the structure model is ready, and we need to generate the load component for the trust application. Trust methodology wise, we presented several times in the conference. So we are using the load component method. So that's why we are using we need to generate the load component for structure model. And using the trust input manager, we set up all the analysis folder, and it's ready to run all the trust and ILA run. So using the supercomputer or PC, we need to run the ILA for the selected the load case file. And then once the ILA is completed, then we can run the trust to synthesize all the structure response. And once the trust execution is completed, we need to perform the post-processor to extract some key parameter index from the result from the ILA and also structure response. This assessment stages, we can check the hull response for the KPI, the key parameter index like hull motion, acceleration, and mooring line tension. And also the post-processor provide a fatigue assessment on the mooring, and definitely trust generate the stress signal. Using this signal, the structural assessment can be done, like for the strength analysis, fatigue assessment, and also buckling assessment. And after assessment is done, the structural engineers check that this structural response and also hull response satisfy the criteria. If not, they need to change the hull configuration, modification, and then we can do the roof. That's the whole loop of the analysis. So I'd like to say that each discipline means that the naval architect or structure engineer, they need to prepare this model, ILA model and structure model separately. As trust tools to doing the integration with the ILA result and the structure model. The more detailed ILA cases, for example, the OpenFAST modeler, can be done by the naval architect or mooring engineer. They provide the hydrodynamic model for substructure. Usually we are using the WAMI model, and the Morrison model cases, they can use a CFD to validate this Morrison and the coefficient. And the rotor and nacelle assembly model and the controller models should be validated according to the vendor data. And according to the in-place conditions, the mooring design should be done. The structure model, the structure engineer prepared the structure model with the commercial tools like ANSYS or Nastran and Abacus. So for the steel structure cases, they are modeled the structure with the shell and beam element combination. For balanced water cases, conventionally we are using the mass element model, but we can apply the pressure mapping also. And they need to define some connection node point, like a fairless connection, power load connection, and the power cable connection. They specify this nodal point and element specification in the finite element system. So this is an overview of the trust work progress. So using the trust input manager, the input manager generates the folder structure. So folder structure has a 01 modeling folder, 02 rate case folder, 03 is a trust folder, 04 is the post-processing folder. So when you initiate the trust input manager, you can specify the interface, YAM file, and the project, and software, and trust YAM file separately. And then using these 4 input files, and in the modeling folder, the neighbor architect lead, they need to put some ILA model in this folder. Structuralist engineer, they need to put some structure model in the FE model. Then trust to read this information using these 4 YAM file. They can do the rest of the things, like the ILA pressure mapping file. Using the pressure mapping file, read the FE information. They generate the hydrodynamic pressure mapping file to the WAMI. And once WAMI is done, then extract the pressure loading to the structure model. And for each load component cases, structure models solve this load component and generate the output as a load response folder. And once this input file is ready, the pre-processing, then we are ready to run the trust. Before run the trust, we need to set up the load case file. I will show you in the detail in the demonstration file, each one. The load case file, you need to specify the ULS or FLS load cases. So load cases file contains the wind data, wave data, and current information for the corresponding load cases. And up to 1 and 2, the folder is set up. Then trust folder, you can run the serially. The first one is that run TopSim to generate the wind environment for the turbulence wind environment. Turbulence wind environment read this load case file and the corresponding wind data and generate the wind field automatically. And once the TopSim run is done, then you can run the second one, OpenFAST. OpenFAST run is generated all the inputs from the load case file into the trust folder and automatically generated OpenFAST input corresponding environment condition and automatically run according to the number of the CPU sensor, CPU or parallel option. And once the OpenFAST run is completed, then you can run the trust. The trust to read this OpenFAST result and the structural response and generate the time history of the stress. And up to 3 levels completed, then you can run post-process. Post-processors read the OpenFAST result and the trust result and generate the summary file. Each load cases, it summarized all the KPI response, the extreme statics and other the statistical quantities are printed out. And also the output is the summary spreadsheet or the graphical contour plot is also generated. And optionally, you can run the file, the OpenFAST pre-screener. The OpenFAST pre-screener read the OpenFAST output file and then assess some specific estimation like mooring strength and fatigue assessment, and also some optional structural fatigue assessment without running the actual final element analysis. This is the optional process. So the post-processor and the OpenFAST pre-screening is the post-processing. So all the post-processing results stored in the number 4 post-assessment folder. So number 3 is the raw data for the execution. Number 4 is the summary folder. You can think about it. So using the class rule checkup software, so access to this output file, we can estimate some class code checks like buckling or strength and fatigue assessment. That's a whole overall picture of the trust workflows. And the provided demonstration is a 15 megawatt the generic semi-submersible structure. So it is very similar to the Windmoor project. So 3-column semi, and the size is summarized like here. And also he applied at some Y shape, the mooring line. The water depth is 140 meter. It's applied. And structural model is also preliminarily provided. This is structural model made by the Nastran format. So the balanced water is applied with the mass matrix, so directional mass, concentrated mass, and boundary condition is applied, and mooring and tower interface is modeled. This structure is the off-centered tower model. So east column has the power connection. And using the Patron, so extract the wetted surface area for the pressure mapping. So that called the wetted surface.scs file is generated. And the column and pontoon, the Morrison member is modeled. So the corresponding Morrison member element is separately prepared in the Patron format. So later, using the OpenFAST output for corresponding Morrison member load, it directly mapping to the structural model for the wetted surface area. So that's an overall demonstration explanations. I will go to the actual file, and then I will do the execution. So let me go to the folder like this. It's a little bit smaller, right? So first of all, you need to prepare some working folder. Currently, we call it demo folder. The demo folder has two prepared folder name is the modeling and load case. The modeling folder, you need to put some FE model. FE model folder, structure engineer already prepared the structure model here. This is the Nastran file format. Structure model info file is here. And the wetted surface area grouping file is already prepared. This wetted surface area grouping file used for the pressure mapping on the wetted surface area to get the hydrodynamic pressure loading. Morris.
Sorry to interrupt it. You're muted?
Oh, yeah, I thought it was just with me.
Jason and John, you're muted on the trust side.
Oh, I'm sorry. Oops. Oh, I didn't
No
recognize.
worries. You got muted at the Morrison file explanation, so it wasn't too far.
Yes, like 1 minute only.
Oh,
Yeah, so not bad.
Oh, I see. Morrison modeling.
No. Just at your Morrison
Actual
file.
Okay. Okay.
So it was just for the last file you showed. Yes.
Okay. Okay. So I think that this is too small. Okay. Too small. So I will make it more bigger. 225. It's a better, right? Yeah. It's better to see. Okay, structural engineer. Can you hear me?
Yes.
Oh yeah, that's great. Okay. So structural engineer prepared some structure related input file. First thing is that the structure model itself, this is an abstract format. And second thing is that they need to specify which element is for wetted surface area. This is an abstract file format. And Morrison element should be specified. So inside of this selected group file, it looks like this. It's a set of elements corresponding to the wetted surface area. And also Morrison case, Morrison element, or specify that. The Morrison element name is like this: Morrison pontoon side north, column side east, like this. That's all input file. And next one is that the OpenFAST input template. So OpenFAST template this is an example. So this folder contains the aerodynamic coefficient file and the beam line and blade information and aerofoil geometry file and coefficient files. This folder does not change any input. The main folder usually change the input file, like inflow, they change the wind velocity and direction. Elastodyne is the initial condition, or other the blade pitch angle, yaw direction, that kind of things. Elastodyne tower, it does not change. Tower related information is specified. Hydrodyne is the wave condition and current condition is specified. Mooredyne is a mooring line condition, and servodyne is the controller. And the other folder is the topsim folder. Topsim is used for generating the wind environment, for turbulent wind environment. So it can be changed for the different wind speed and the turbulent condition. So that's a template is specified in the IALA folder. And once this modeling folder is ready, or even the load case file is ready, load case file looks like this. The CSV file format. So when you do the wind turbine analysis, you need to specify the load case for the specific application, like FLS, fatigue state. You need to put all the scatter diagram in the load case file. This is a serial number, for example. And second column is the TLC, because we need to specify the TLC, because that according to the TLC, the turbine controller setup is changed. So that's why we need to specify that. And wind type is normal turbulence model, extreme wind model, that kind of things you need to specify that. And wind speed, definitely you need to specify, and wind direction, and wave, HS, and TP, and gamma. This is Jones spectrum. and wave direction, current speed, and current direction. And number of seed numbers, the number of realization. So if you put it 1, so automatically 1 realization is generated. If you 10, so this package generates the 10 realization by changing the random seed number automatically. And the total simulation time and the yaw angle. This is the nacelle yaw angle. Now is the wind direction as nacelle yaw is the same. So it's the aligned case, but sometimes yaw misalignment is required. So you need to put some different heading angles here. And this load case file, you can specify the other component optionally. TI is the specific the turbulence intensity in %TC, and this one is a power law for the wind spectrum, and probability is that used for the fatigue assessment for the fatigue beams. And the other options are, for example, the shutdown case. You can specify the shutdown instance time, and when you shut down, the pitch angle speed can be specified, and the final angle of the pitch can be specified. So that's optional, you can put it. But in this demonstration is the list. Yeah. So that's the input is ready. Then you can just run the input manager. Then input manager automatically generates the other folders with some information. To run the input manager, so you need to set up these 4 input files. I will show you that one by one. First one is the project YAM file. Project YAM is specifying it's kind of the node. So this folder project, what project names will be used, ILA model and the FE model, what can be used, and the other record purpose, you can put some the version and revision number, revision times, you can put it. And you need to specify the project folder. So this project folder is the demo folder, so you can put it demo. And also what turbine spec was used, you can specify. And floating, the substructure wise, some record, you need to specify that. And the site information and the common constant like gravitational acceleration and the water density, water depths, you need to specify. That's a project information. And interface information is that specify the hull geometry in the hydrodynamic coefficient because we are using the WAMIT. This is the WAMIT panel information. And the turbine top sim input template location. The turbine input template name is this one. This is provided in the modeling folder. And OpenFAST template name. So modeling, ILA model, the template name is this one. So you can just specify that. And the FE model. So go to the FE model folder. Structure engineer provided this Nastran model underbar model data. So you can specify. And weighted surface area, the group file name, you need to specify. And then FE model and the ILA model, they need to interactively cross-check. For example, FE model, they need to specify the wind node ID number. So 6 DOF, the tower base load will be transferred to this point in the FE model, so they can be specified. Acceleration is the center of gravity, the ID number. Then using this ID number, later the trust generated load components for the acceleration, so around this point. And the mooring load in the structural model, so you can, this is the 6 failed locations there. So 6 failed corresponding the element numbers specified. Recently, the Morrison load is added in the trust module, so that's why this is optionally. You can consider the Morrison load on the structure, yes or no. And if you apply the Morrison load, then you can specify the Morrison surface element group file to specify that. And the software license is the trust is a couple of the software, the packages work together. So for example, analysis software, you need to specify the trust WAMIT executable. Where is the WAMIT executable there? And TOPSIN executable, and OpenFAST executable, and trust itself executable location. And utility software is the batch runners. So WAMIT generator means that it reads some basic information, generates WAMIT panel. That's the WAMIT panel generator. So, but anyway, this software name is almost fixed. So only different is that the folder name. So you need to specify some folder name when you use these packages. And units, you need to specify, but it also almost fixes it. So you can use it as it is. The last one is the trust. Trust is the load case definition. So we currently we are dealing with the two different load case, ULS and FLS. Later we can expand the different load cases. So for example, ULS, the strength analysis case. So load case, where is the load case file located? So load case file 02 load case folder, we put the load case demo ULS CSV file is put on there. And total simulation time you can specify. And sometimes the simulation is done, and then we can do some resampling. So if you need a resampling result, then specify the resampling time step. And also the strength and fatigue assessment for structure, we follow the DMV, the LRFD format. So that's why you specify the factor for dynamic and the static LRFD factor. Then result will follow that applied this LRFD factor. And the ULS and FLS, so when you run the trust, automatically read this file and then execute. So if you make it execution true, then automation read this file and then automatically execute these ULS cases. If you take a false, does not run. Yeah. This is a workflow control. Workflow control is just two options. One is that how many CPUs are used. So currently I put 8 CPU, and it can be run or not. So we'll run all the things. That's why we put it true. So TOPSIM will run 8 CPUs, OpenFAST also 8 CPU, Trust also 8 CPU. And OpenFAST pre-screener is optionally run for the boring fatigue assessment and also pre-screening of the stress, the structure stress without actual running of the finite element system. So this optionally can do. You can specify how many CPUs can be used, and pre-screening done for the selective range of the analysis file. And some info files you need to specify. Detailed things will be given in the more detailed training course. So those information is put in there. The only thing to do is that just run the Trust Manager. And Trust Manager automatically generates the rest of the folder. So modeling and the load case file already made. And the trust folder is now made. So it has a two folder, ULS and FLS folder. and all the the required input files are generated automatically. So all you need to do is that go to the trust actual folder, for example, ULS. First thing to do is to generate the TopSim input file, and then I'll put it there. Then TopSim, when you click this run TopSim, the corresponding ULS load cases, the load case here, ULS load case, read this load case file, the corresponding wind data is generated. This wind data is used for the ILA analysis. Since I put the 8 CPUs, so load case is only 2, so 2 cases are generated. You can find the generated wind data in the trust folder, wind data folder. So separately, BTS file. BTS file is out from the TopSim. It's generated. And next thing is that OpenFAST run. Then this OpenFAST packages with the template file and also load case file. It generates the corresponding OpenFAST input file in the folder. So automatically generate and even run. When run, we specified 8 CPUs. So at one time, it has 8 cases are running. OpenFAST run takes a little bit time, so I will close it. So I made another folder for the same things. So this folder is already run the OpenFAST out. This OpenFAST run for 4,800 seconds with the 0.02 second difference. Time step is already there. So OpenFAST is run, and next step is the trust. Trust run. When you click this trust run, read the OpenFAST result, and with the structure information, it generates the time series of the stress. So I will show you that how fast of this trust synthesizing. So because there's already a result, so the trust, if there's a result there, it does not run. So that's why I removed this trust folder. So I will click the trust. This is time domain structural analysis. So first thing is that read the load component file, and then start the synthesizing for strength analysis. Synthesizing means that read the ILA data from the OpenFAST result, and then using the corresponding Hall response, we call it Rodal response, and then generate the time history of the stress component for every element. Currently, we have a structural model with 26,896 elements. So for this element, it's a synthesizing is done. So we are using the 8 CPUs. So this is a 4,800 second with the 0.02 second time step synthesizing. And roughly it takes 1 minute 20 seconds. The OpenFAST run for this 4,800 second OpenFAST run takes around 40 minutes, but structural analysis takes 1 minute, 1 or 2 minutes. So once the stress is synthesized and using this synthesized result, it has an output, make an output. So let's go to the output folder. So it generated trust folder. According to the strength analysis and fatigue analysis, they make a different folder name, synthesize the common name. So now this is ULS, strength analysis. So strength output is like this. So we provide the maximum, the strength analysis. We provide the formless stress output from the overall time history for each element. So there's a contour plot in terms of the F06 file format. This is the Nastran file format. So it looks like this. So using the class tools, can read this output file, then easily see the formless stress control. Or CSV file, can see the summary for each element. The summary looks like this. This is a serial number, so actual element number, and this is a 1 hour simulation. So from the 1 hour simulations, the maximum formless stress is like this. When to happen? So this is the time of the instance. So total 26,900. Yeah, this kind of the element summaries here. And the other output is that contour map. So it provides the trust package printed out the VTP file for contour map for the corresponding the load cases. So you can use a ParaView. This is the open source program, and then show that the contour of the output like this. This is the formless stress contour for the corresponding load cases. So you can see the outer shell or change the opacity. Then you can see the inside the shell also, internal members stress variation like this. Okay, this is a one single run, and then if you run the post processor, then read all the ILA and trust output, summarize the result. So because the output is a heavy number, so we also apply the multi-processing for the post processor. So the number for post-processed output, this is a ULS. So output files like this, little bit detailed. So if we want to see the very detailed output, for example, the whole strength summary for each state, then CSV file shows that all the executed load case summarize the result. So for OpenFAST cases, we specify the key parameter. For example, the blade deformation, wave elevation, tower base moment and shear force, and hull motion. So you can see for the statistic output can be found. So for example, this is load case number 1, load case number 2, load case number 3. But each load case has a 2 realization, 1, 2. So this is the raw data, and this one is that using this raw data is why Gumbel fitted 3-hour maximum values fitted. Yeah, showing that like this. Gumbel fit or Vibe fit is optional, you can choose it. And also upper part is the ILA result, lower part is the element result. So this is the ULS, the formless stress extreme values printed summarized like this. So engineer can use this detailed information for their assessment, or this is too heavy, in this case, you can use the summarize the contour map visualization. It's called it all DLC VM stress VTP file. So when you go to this VTP file, then you can see like this. Magnify. Fire, yes. Let's see, yeah. Because this is a summary, so the VTP file. So summarize all the contour maps. So since we run the 3 load cases, each load cases contour you can see, or all the load cases maximum contours you can see here. And how can he exit this one here? Yes, and if you click this one, and this is triangular, you can put it somewhere like this. Then summary file shows up. So as you can see, maximum, you can see the fourth line is what is the element ID, and fifth line is the maximum form stress is 89.8 megapascal, and the sixth line is that when to occur is that load case 3 has this maximum value, that kind of things. So graphically, the engineer can check the statistics. Okay, for the fatigue assessment, the same thing. So go to the 3 folder, fatigue assessment. So you can run the 1, 2, 3, 4, 5, 6 serially. And then post-processing output file, this looks like this. And the fatigue damage also the same. So go to the VTP file contour map. This is strength. This is fatigue. Yes. Fatigue is looks like this. Yeah. And images, right? For example, so fatigue. Now we are fatigue live or fatigue damage. You can choose it. So you can see that the control map, and also click the triangular shape for some specific point. You can see some summary like this. That's a graphic output. And similarly, you can see the summary output like this. For example, fatigue damage summary, or it's like this. Select the element cases. So fatigue damage for the load case. This is the load case. This is the load case, and how the fatigue damage looks like this. You can check, but when fatigue load beam is a quite huge number, like 500 to the 5,000, so it is very difficult to load this spreadsheet and check all the trend and the statistics. That's why we have another tools that's a dashboard. So output file is copied to this folder, And then if you click the dashboard, for example, the FLS, like this, then browser environment dashboard, this looks like this. So for the PLC, this is the x-axis is the number of the beans. We consider the almost 6,000 beans calculated, and then wind speed and wind direction, so summarized, and then some KPI probability. This is the probability weight, and Nusselt acceleration variation, and generation power, and extreme value, and left-hand side is the indicator for the check of the design constraint is matched to meet the satisfy the design criteria or not. Check that. Yeah, heat angle max and the heat angle mean value. These items, you can choose it. So this is a selected item. If we want to add another item, then we can select the some available items, whatever. So for example, like this, and then add up the last line. Add up the last line of this kind of things. This is using this the dashboard. You can see some trend or extreme value. Where is the extreme value happen, and what years is the problem? You can find it. That's the one thing. The other one is that heat map. Yeah, this is a heat map. Heat map shows that some correlation. So, for example, the Nusselt acceleration variation according to the wind direction versus wind speed. If we want to change this axis, like wind speed versus wave height, then because it has more than it's around the 6,000 cases, it's really time to loading. Wow, very huge size. Maybe it has a time. Yeah, it's wind direction versus wave direction. For example, wave direction. Yes, this kind of things. So if you want to check the correlation between the two parameters, the wave direction versus wind direction, for example, Nusselt acceleration, where is the critical? So you can check that from this all summarized data. That's a dashboard capability. Yeah, up to now, so very quickly, it's very quick. So usually the trust training takes at least 1 day to explain that all the input parameters and some option and some very detailed information. So we have only one hour demonstrations. I can just show that some execution and what is the output for the critical things. Yeah. So is there any question from this demonstration, or then can speak up? Yeah. Hello, is there any question on the demonstration?
Yeah, I have a
Yeah.
easy question. I've seen in the input files you can choose between OpenFAST and OrcaFlex. So that means you can do the same procedure using OrcaFlex.
Almost the same. Yeah, almost the same. OpenFAST cases, we have some automation. We made some automation. OrcaFlex wise, slightly, yeah, we can easily implement automation. It's almost the same procedure.
Okay. Yeah, maybe the preprocessor is better for the OpenFAST, right? In terms of creating input files, etc. These are a bit different in the OrcaFlex, maybe that you don't have.
Right. Yeah. The Python-based script can be used. So the with the OrcaFlex sync file and they extract the result. Yeah, that's can be automated. Right.
Okay. And in this demonstrator, did you use ANSYS also at the same time?
ANSYS originally when we developed the trust, we used the ANSYS. So yeah, it can be used, but we are thinking about some unified input structure for any finite element system. So through the JIP, we will develop this input structure. So whatever FE model, so output provide the that file format, then no problem. Yeah, any FE model can be used. Now in this procedure, we just read directly the raster output model OP2 file. But yeah, it can be standardized later. Yeah.
Dan, this is Rick. I probably missed this from the beginning of the presentation, but could you confirm how the external pressures are calculated? Starting, my question would be from what data are you getting from the OpenFAST output, and then how do you go from there to getting the pressures to be mapped onto your structural model?
Yeah, so pressure mapping wise, we need a weighted surface area, the pressure mapping file. So procedures that using the structure model, so weighted surface area element file set is extracted, corresponding data point mapping to the WAMIT. So WAMIT calculates the corresponding the structure nodal point pressure. And then later, this WAMIT pressure output mapping to the structure directly at the corresponding element.
Got it. Thank you. So are you getting then like the surface elevation as an input then that gets passed to WAMIT? Time step by time step, or?
No, not step by step. So this is a linear line pressure mapping. So below that the mean water level, the pressure mapping pre-processed.
Okay.
This is the same as the OpenFAST analysis. OpenFAST using the pressure mapping below that the mean water level using the WAMIT pressure output, right?
Yep.
Yeah, same pressure mapping to the structure in the pre-processing, and later using the wave elevation, it generates the structural response directly.
Got it. Thank you. So yeah, appreciate it.
Thank you. So other question on this is very short, just lots of things to talk, but it's very limited time.
Will the video recording be made available after the session? It'd be good to kind of, I guess, review and reabsorb some of the information.
Okay, yeah, I will upload this video recording and let you know. It can be shared.
Okay, thank you.
You're welcome. Is there any other question or suggestion? We have a peer session, even though you are joined the online, but if we have got time, yeah, please join the peer session. So location is Bamshar. It's close to the Fry Road and I-10. Yeah, close by there is a Sam's Club. Yeah, so yeah, please join the peer session, and then you can raise a question additionally at the time. Yeah.
Yeah, since I'm in Europe, I'm not able to join the beers, but I have a last question. In this structural analysis, you showed the result in Paraview. That was a shell model, right?
Yes.
Okay. I'm not a very structural person. That's why I ask. Thank you.
Yeah. So this is a finite element model. Is sometimes it's global model. It's a very coarse mesh, and for the hotspot analysis, more detailed analysis, it's a very fine mesh system. So depending on this detailness, the trust can synthesize all the structural response.
Mm-hmm. Right. Then thank you very much for the demo.
Yeah.
I think I drop, but
thanks for joining. Appreciate it. Yeah. Okay, so is there any further discussion? Otherwise, yeah, I think that we can close the meeting, and all the recorded video will be available in the share folder. We will send some link, through the email.
Great. Thank you for all the effort that was put into this and for the presentation.
Thank you. Thank you for joining, and see you soon. Yeah.
Thank you.
Thank you. Thank you, everybody. Yeah.
Thank you, everyone.
Thank you.
Thank you.